Okay, so all the language models that we're familiar with, like Llama or GPT, okay, they all have one thing in common. Namely, they're all based on the transformer architecture. This type of neural network was initially proposed in a paper back in 2017. And since then, transformers have been able to achieve state-of-the-art performance across a wide variety of NLP tasks, the most well-known probably being chatbots, but also tasks outside of NLP, like time series forecasting. And the main breakthrough that allowed transformers to be so successful was hinted in the title of that paper. It's because of a mechanism called neural attention. This is a simple but powerful idea, which was partially inspired by how the human brain works. We know that when we read a sentence, not all the words are equally important for understanding the meaning of that sentence, and our brain is focusing more on certain words which are more relevant and ignoring other words which are less significant. The attention mechanism was designed to allow transformers to do the same thing with data. Not all the input features, not all the input information that a model receives is equally useful for solving its task. So the model learns that it should pay more attention to certain input features and less attention to other features. Now, before going further into the details of the attention mechanism, it would be useful to first say a few words about how language models usually process textual data. So neural networks cannot work directly with words. They can only understand numbers. So there has to be a way of converting strings of text into some kind of numerical representation. The first step in doing this is called tokenization or token encoding. This is the process of splitting a paragraph of text into smaller units called tokens. A token can be either a word, a subword, or even an individual character. For example, the OpenAI website provides a simple tool that allows us to visualize how tokenization is done by their models. Here, each color represents an individual token, and these are the main tokenization rules. So the words that are the most common in a language usually get to have their own tokens. In the case of those words that are larger or composed, they are split into meaningful subwords like prefix and suffix. And if a word is a little bit more unusual or spelled wrong, then it can be divided into even more tokens like individual syllables or characters. Of course, different tokenizers will have slightly different rules, but this will be the main idea. After tokenization, the next step is called vector embedding. This is the process of converting tokens into vectors of real numbers. These vectors are usually high dimensional with the typical dimensions of the order of hundreds or even thousands, depending on the vocabulary size. We can think of each dimension as representing some kind of characteristic of the embedded word. Like one dimension could represent gender, another dimension could be height or species, and so on. The numerical values of the vectors are learned during the training process. And in order for an embedding to make sense, it needs to satisfy a few basic properties. The most important one is that the geometric relationship between any two vectors should reflect the semantic relationship between the corresponding words. So this means that if two words have similar meanings, if they are synonyms, then they should be embedded into vectors that are close to each other in this vector space. And also, if two vectors are far away, then they should correspond to words that are not related. And more generally, we say that the distance between vectors that represent the same concept should be the same. So the distance between dog and wolf should be the same as the distance between cat and tiger, because they both represent the concept of going from domestic to wild animal. So these kind of properties are useful for an embedding to have, but it's still not enough because of a problem called polysemy. This is when a word can have several different meanings depending on the context. And with a simple embedding, the problem is that all the different meanings of the same word would be mapped on the same vector representation. And that's not ideal. It would be preferable to have a smarter embedding where different meanings of a word are mapped on different vectors depending on the context. And that's where the idea of self-attention comes in. So to be more specific, self-attention is a mechanism by which we take an initial vector that doesn't know anything about its larger context, and we use the surrounding words to transform it into a vector that is context-aware. There is a quote by a British linguist from the 50s who said, "You shall know a word by the company it keeps." And that's basically what self-attention is doing. So let's say we have this sentence made out of these tokens, and those are the initial vector embeddings. The word station could have several different meanings. It could be either a bus station, or a radio station, or a gas station. And we would like to convert it into a vector that refers specifically to train station. The first step is to compute something called the attention scores between the word station and all the other words in the sentence. The attention score can be interpreted as a number that tells us how related are two words with each other within a given context. And it is obtained by computing the dot product between those vectors. So here we see that for station, the word that has the highest attention score, apart from a station itself, is the word train, as would be expected. Then the next step is to normalize the attention scores using the softmax function. Then we multiply the attention scores by their corresponding vectors and sum them up. So in other words, we are computing a weighted average of the initial vectors, and those vectors that are the most relevant for station will make the biggest contribution to this average because they have the largest weights. The final result is the new embedding for station, which contains within it part of the initial embedding for train, and that's why we say that this new vector is now context aware. And of course, we don't do this for just one word. We repeat the transformation for all the words in the sentence. So we combine all possible pairs of words. We compute the attention scores for all of them. In this case, the attention scores can be arranged in the shape of a matrix. And then we compute the weighted average of the initial tokens along each column, and we get the new context-aware vectors of our initial tokens. There is also another type of attention called masked self-attention, which is used to solve a different kind of problem. So in this case, the task is to use the first n tokens in a sentence to predict the next one. For this, the attention matrix is modified to have this triangular shape because for each word that we're trying to predict, we can only use the words that are before it in a sentence. We cannot use the words themselves or the words that come after it. So if we want to predict the second token, we can only consider the first one. If we want to predict the third token, we can only attend to the first two, and so on. This kind of masked self-attention is not used by all the transformers. It's only needed for those transformers that focus on text generation, like GPT, where the model has access to the previously generated tokens, and it has to learn how to use them to generate the next one. Other transformers like BERT, which focus on text classification, don't require masked attention. Now, in both previous examples, there was one important element which was missing. There were no trainable parameters that the neural network can learn. It was just a straightforward computation. So that's why the full version of self-attention is modified to also include 3 dense layers, which are updated during training with backpropagation. The initial vectors are passed through these layers and projected on 3 vectors called query, key, and value vectors. These names are in analogy with information retrieval systems. So usually when a user enters a query in a database, the query is matched against a list of key value pairs. And for those keys that are the most relevant for the query, the system returns the corresponding values. And this is basically what happens with the vectors. So the query vector is matched against the key vectors. This is done by computing the dot product and getting the attention scores. The attention scores tells us which keys are the most relevant for the query, and then we compute the weighted average of the value vectors using the attention scores as weights. So it's relatively similar to what was before. This entire ensemble is called an attention head. Now, it's not possible for a single head with 3 dense layers to learn all the patterns that exist within a language. That would be too much. So that's why the full version of the attention. So that's why in practice transformers don't use just one head, but instead they train several attention heads in parallel. So each head receives the same input as all the other ones. They independently perform the key query value computation. The outputs from all the heads are concatenated into a vector, which is then passed through another dense layer, so that the final output vector has the same shape as the initial input vectors. This is what's called multi-head attention. Because each head is independent from the other ones, this means that each head can learn a certain feature from the tokens. Like one head can learn to identify punctuation signs in a sentence, or verbs, or acronyms, and so on. This is similar to what happens in computer vision with convolutional neural networks. So a convolutional layer has several kernels, and during training, each kernel learns a certain pattern from the images. Which could be either a circle or a straight line. And the multi-head attention is like the NLP analog of that idea. And another advantage of using independent heads is the fact that they can be trained in parallel, which is something that couldn't be done with recursive neural networks. Okay, and then zooming out, the multi-head attention is the main building block of is the main component of a larger building block of the transformer. This building block can be one of two kinds, either an encoder, like the one on the left, or an decoder, like the one on the right. So in the case of those transformers that use both encoders and decoders, a typical task would be a language translation, which was also the task used in the initial paper from 2017. So it would be like this: the encoder receives the input sentence that needs to be translated, and it converts it into an intermediate representation. We see that the encoder doesn't have masked self-attention because it's not trying to generate additional text. It's just learning all the dependencies between the vectors of the input sentence, and is turning them into a reasonable representation of the sentence as a whole, which is then given to the decoder. And then the decoder, on the other hand, does have masked self-attention, because during training it receives the correct translation as input, and it learns how to predict each word by using the previous words from that sentence. And it's not mandatory for a transformer to have both encoders and decoders. It's also possible to have transformers made only of encoders, like BERT, or decoders, only like the models from the GPT series. Okay, here are a few more examples of transformers from each of the three categories, and the task that they specialize on. So there are a few tools that allow us to visualize how the attention mechanism looks like in various transformers, and how the tokens of an input sentence attend to each other. One such example is called XBERT. This is available as, it can be accessed either as an online interface, or it can also be downloaded and installed locally. So we can, from the first row, we can select the transformer, the kind of transformer that we're interested in. In this case, selected BERT. On the second row, we can provide a sentence that is given as input to the model. And then from this horizontal slider, we can select one of the layers. So BERT is basically a stack of 12 encoder blocks, and so each one of those is a layer. And in each layer, we see the attention patterns of all the heads in that particular layer. Then we can also select a particular layer, and then look at the individual heads in that layer. So again, each layer has 12 heads. In the case of BERT, each one of those vertical lines represents a head, and we can just slide the mouse along the lines and see the attention patterns for that particular head. And then you can also fix a layer and a head and go through each individual token in that head, and see how they attend to each other. So the purple line represents the value of the attention score, and so a thick line will be a high attention score, a thin line will be a low attention score. So the first thing that we notice here is that because it's BERT and it's an encoder only, the tokens attend to, so the tokens on the right are the ones that are paying attention. Sorry, the ones on the left are the ones that are paying attention, and the ones on the right are being attended to. So here we see that the tokens, each token is paying attention to the tokens that come before it as well as after it, because BERT is not using masking. This is in contrast to, for example, so here I've changed it to GPT-2, which is decoder only. And so here we see that the tokens are paying attention only to the tokens that come before it, but not after it, because GPT is being a decoder only, is using masking. So this would be one difference between them. So it's called BERT, but it's not limited only to the BERT model. It works more or less with any transformer that is open source and available on Hugging Face. And here I'm using GPT-2 because it's the last one from the GPT series that was open sourced. So now, by looking at the various attention heads, we can observe various patterns that the model has learned during training. So, for example, so here is a simple pattern where each token is paying attention to the next token in the sentence. Similarly, this is a pattern where each token is paying attention to the previous tokens. So they're focusing on the order. This is an example of an attention head, which is focusing mostly on the verbs in that sentence. So it's learning to identify verbs. Yeah, I think this one is a little bit more interesting. So here, the attention head is learning to focus to the meaning of acronyms. So it's identifying the acronym with the words that correspond to it. It's similar to what happens in convolutional neural networks, where the low-level layers focus on simple patterns and the high-level layers learn more complicated patterns. And then we can also see if the vectors are really context-aware by verifying how the model pays attention to the pronouns. So, for example, here we have the sentence, the dog did not cross the street because it was too tired. We see that it is paying attention to the dog. So the model knows that it is referring to the dog. And if we change just one word in the sentence and replace tired with busy, and again ask the model who is it referring to, the model is able to figure out that this time it is referring to the street. So it's not the dog that is too busy, it's the street, as would be expected. So basically we can see that the model is adapting depending on the input, is adapting the attention scores as the input changes. And we can use the same trick to see if the model has learned any kind of biases during training, like gender bias. So for example, here we see the sentence, the doctor asked the nurse a question about his patient, and we can see that his token is paying attention to the doctor. So the model is associating his with the word doctor. And if we replace his with her and try again, so this time we see that her is paying attention to nurse, which is not great, because this basically means that unfortunately the model has learned, this particular attention head has learned the bias that doctors are usually males and nurses are usually women, which is not what you want to see in a model. So this would suggest that you might want to retrain the model or fine-tune it with more examples where nurses are males and doctors are females. So this was XBERT. There is also another similar tool called BERTviz, which again is not limited only to BERT. So it has several features. This one is actually similar to the previous one. Again, it allows us to see what's happening inside the particular head. The horizontal slider represents the heads in a layer. And then there's also the vertical slider that allows us to select the different layers. And then again, we can go over each head and see how they are paying attention to the tokens. Then it also has, so this is called the head view because you're seeing a particular head. it also has something called the model view, which is giving you a high-level view of the entire model. So here you can see all the heads at once. So the columns represent the heads, and the rows represent the layers, and it shows you, it gives you a high-level view of how they all look. And you can also you also have the possibility to click on a particular head and see more closely how it looks like, all the attention patterns in that head. And so it also has finally, it also has something called neuron view, which this one is basically showing you what happens, how the query key value computation is performed. So here it's showing you, so the first column represents the query vectors that I was mentioning earlier for each token. The second column is the key vectors for each token. This model here is GPT-2, so that's why it's only paying attention to the tokens before it. Then the third column represents the element-wise product between the first two. So here, each one of those vertical bars represents a number. Blue is going to mean a high value, and orange is going to mean a low value. And then on the third column, if most of them are blue, then the dot product is also going to be blue. And similarly, if most of them are orange, then the dot product is going to be orange or a low value. And this kind of shows you how these attention scores are computed. This feature is a little bit more limited because it doesn't work with doesn't really work with all the transformers. It's I think it only works with BERT and GPT-2 and a few more. But the previous views, model and head view, they work with anything that's any transformer available on Hugging Face. So I've included here a few more links to where these tools can be accessed. And yeah, I think this was all I wanted to mention. So yeah, thank you for your attention.
Thank you, Catalin, very much. Do you have some questions? Yeah, just wait for the microphone.
So I was wondering, in your doctor and nurse example, because the sentence is ambiguous, what would a good solution look like? Would it be equal weights?
Yeah, exactly. So yeah, there are. I have been able to find other heads where the model where the his or her. I made it ambiguous on purpose. And so if it's not biased, then you would like to see that it goes to both of them. Not necessarily in this case, it was a very thick line going to one of them. You would like to see a thin line going to both of them. So that shows you that the model is not entirely sure which one is pointing to. That's how an unbiased attention head you would expect to look like.
Thank you.
Somebody else? Yes.
Well, thanks. I was wondering if the similar approach can be used in the field of vision transformers.
There's actually a question on the GitHub repository for BERTviz, and so the guy who implemented the tool said yes, it is possible to, in theory, it is possible to do this, but so far it hasn't been implemented. So yeah, in theory it's possible, but as far as I know, it hasn't been done yet for vision transformers.
Thanks.
Do you have some more questions? No, that's it. Thank you very much.
Thank you.